Hello everyone, my name is Sabet and I'm representing a simple low-cost approach to detect hand gesture based on software event camera emulation paper. We use embedded systems as system on chip in many devices, and every day companies release new microcontrollers and SoC for use in embedded systems. Even today, image processing and working with visual data is costly in embedded systems. Cost is an integral part of the designing system for industries, and we are always looking for solutions that reduce cost. Raspberry Pi is one of those systems that is frequently used in many projects which has significant processing power. It can even perform image processing, but we don't usually use one system for one application. For example, in a smart management system, we must process different sensor data, handle HMI for our users, and collect useful data into a local database. In this system, heavy processing may cause failure. In this research, we tried to find a new approach to handling visual data in SoCs like Raspberry Pi with very low load on the CPU and simple algorithms. In order to achieve this, we do not process normal frames but instead use events. However, due to the price of event camera, we do not actually use the event cameras. In our research, first we tried existing simulation of the event camera and selected one of them for our work. However, we needed to optimize this algorithm for SoC like Raspberry Pi so that it can be run in acceptable time. In our second part of the research, we introduced some algorithms that can be used by this emulator for detecting hand gestures. Before we present this paper, we will talk about the basics of event cameras. In simple terms, an event camera is a camera that does not work like an old traditional camera. It has a circuit behind each pixel that saves the previous value of that pixel and compares the newly measured value to that. If the change exceeds the threshold, that pixel generates an event packet containing the timestamp, direction, and coordinates of the change. With this approach, each pixel works individually and output data is just the events of the triggered pixels. This means low bandwidth utilization for low scene changes. It provides a very low latency due to very high response time of each pixel. However, due to the difference between classic and event camera, it's not an accurate comparison. But if we talk about the frame rate, event camera can reach hundreds to thousands of the frames per second, but like it said, there is no frame. Using the output of the event camera requires a different approach for image processing or extracting the frames in order to use them with the old optimized algorithm. Our aim with our research is in two parts. The first is to make an efficient embedded emulator of this camera and have them available for researchers to use them in their algorithms. So, our part of the work is a comprehensive analysis of algorithms and also involve improving Python. We don't want to go for a low-level language like C++. We want to use Python and its benefits. So we can do this by exploiting Python tools and exploring both pros and cons. We focus on the data output of this emulator in the second part of our work. We collect these events and use them as a new process data for our other algorithms, like gesture. In those algorithms, we don't need all the texture. So what if we use that data and extract some meaningful information from it? How well do this approach perform in terms of speed and load when used in embedded systems? These are questions we try to answer in this research, and the short answer is that the results are acceptable. Surely, for hand gesture detection, you can use something like MetaPub and detection a precise gesture on Raspberry Pi with some effort. However, with that implementation, we lose most of our process power. The concept of the simulation is just different between pixel values. But it's not that simple, because we need to simulate all the aspects of the real event camera. But I don't explain them here, and you can refer to the paper that are just about this simulation. You can see the basic steps for simulation here. PyDVS is a Python library that has the building blocks of the emulator for us, so we use that for the rest of the work. There are a number of other libraries that exist and some of them are very powerful. However, for research we don't need that much perception of output and we also need something that our SoCs can handle. If you are interested in learning more about PyDBS, you can refer to its paper and its GitHub repository. For improvement of the efficiency of PyDBS, our focus was on Python tools. For some tools we need to re-implement codes, but some they do the job for us with very small effort. The main tools that we tested were Cython, Numba and CTime, but there is some other tools that can be used like Python. We don't talk about Python here, but in our test it's a good tool and competes with the other. C-type is a built-in library in Python that can wrap the C library for it, in which case you need to rewrite the code in C or use an existing C library and add the headers, then wrap it in the C-type style code. Although this has some downside like requiring a C library or rewriting the Python library in C and exporting a DLL file or shared library for each operating system. The upside is near C code speed. Next is Cython. To use that for a start, you just need a few Python code and it's good to go. It makes C code in the background and use that code to set up for each OS. There is no need for rewriting code, but we don't get the desired efficiency at this point because it can't convert all Python code in an efficient way. We need to rewrite those parts for PyDBS. We rewrite the code to get better result. For example, this is the first try, and you can see it has many calls to Python object, and it took too long to execute that. Cython provides the tool, then check the code and highlight the part that had Python calls in yellow for us, to change the code to use less Python objects. Final results were promising after using also Cython's parallel tool and changing the code. We achieved 2.35 millisecond write time, which is 72% improvement. Numba is a third tool that also uses a just-in-time compiler, so that the first time we run code, it compiles the code and then runs it after that with the compiled code. It doesn't require a compiler step like the others. However, its downside is that most Python modules aren't supported, and we had to spend a great deal of time to figure out how to implement our functions. In addition, we tried OpenCL, but we could not use it on the Raspberry Pi. However, it could be used on the PC and Jetson, and with that we could use GPU power. It has the best performance for PC test, but we had to rewrite the code for it. This slide compares the result of these tools based on the frames that were processed. Maximum frames are 30 frames per second. This frame rate is very low for pure Python, near 30 frames per second. For Cython and C-type the results were similar, and Numba gives acceptable result, but it takes a long time to get a good result from it. This is because of difficulty in implementation. PC result was excellent, like it was accepted. These implementations were very close to each other, because with different implementations we got different results. Next, we will discuss the second part of this research, where we will try to implement an algorithm that can be used with prior results. It is important to note that we test implementation of this algorithm in one system, so we can evaluate their efficiency. Alternatively, we can design the system to be divided in two parts, with one part simulating the events and sending them to the network, while the other collects these events and processes them. Initially, we need a simple algorithm that has a low impact on the code speed but can reduce noise in event data. It is very common for event camera to produce some noise, and even in some simulations, they add some random noise to simulate the behavior of the camera. For more information, refer to the simulation paper like V2E. Before we describe noise filter, first we need to familiarize ourselves with how event data can be processed. There are two main approaches: event by event, which make use of a special algorithm and spark neural networks, Another way is using time slots. We can collect events in, for example, 10 milliseconds and then process those events as a group. We use this method since we use frame-based data and we ensure that data was collected in 30 millisecond window. If we use a higher frame rate, we could change this time slot. During noise reduction, we using a moving window and remove events that are alone based on the number of events under that window. As you can see in this slide, this is a very simple algorithm, but it has a very significant effect. We had clear events after filtering, but lost some of them during the noise reduction step. So we used a morphological filter to extract image-like frames from events. The sample results are shown on this slide. In this step, we must extract object from the two-dimensional array of events described in the last step. Assuming that the camera is not moving, we need to separate region of interest with the contour algorithm. This gave us the most accurate result compared to other approaches. And the threshold based on the size of the array helped us separate different objects in the scene. Our idea was to show the direction of the object movement based on the lighter and darker events in the array. This is because when something moving within the scene, one side of the object forms a lighter event and the other side forms a darker event. Using those equations and how they related to each other, we developed those equations on the paper and calculate the object's moving direction. We need to separate the palm from the detected events and remove the raised portion of the hand in order to detect hand gesture. Therefore, we used the relation between hand parts such as the finger and wrist. We did not need to be precise here as we will use classification in the next step, but this step enables us to obtain better results. In classification, we use CNN with the configuration shown in this slide, with 7 classes for 2,500 samples and 500 samples for testing. These datasets are not very big, but they have very interesting results. During this part of the research, we aim to show how simple CNN behave in such a system without focusing on the artificial intelligence algorithm. Our training data consists only of a single person's hands, but our test data does not. As a part of the test process, we even use child hands. The experiment achieved at least 70% accuracy for each class. Finally, we tested the efficiency of the implementation in runtime for running code on the Raspberry Pi before and after code improvement. Thank you all for your time.